These are the slides for Module B. We're going to be going through the time value of money in this module. We'll be talking about four basic topics: the idea of compounding and its opposite, discounting. We'll be talking about the moving parts of time value of money computations. We'll be talking about annuities, and we'll be talking about how to use your financial calculator. Compounding is a concept most of you are probably familiar with. At some time in your schooling you will have had a conversation around compounding, and sometimes the idea of compounding is presented as interest upon interest. If you were to put a certain amount of money into the bank and let that interest accumulate and add on to the principal that's invested, it's going to grow at a faster and faster rate. If you were to draw a chart of it, it would be an exponential curve which continues to tilt upwards at a faster and faster rate every period. Looking at the arithmetic, if you were to put $100 into the bank and receive 10% annual interest paid at the end of the year, after 1 year, you'd have your $100 plus you'd have 10% of it, so you'd wind up with $110. After 2 years, you'd wind up with that $110 plus another 10% interest, so you'd wind up with $121. And at the end of the third year, you would have started with $121, you would have added 10% of that, and you would have wound up with $133.10. Now, the way I've got it written on the slide has those three kind of stair steps that you can see there, but there are a couple of easier ways that you might write it out. The next bullet point is just $100 times 1 plus 10% times 1 plus 10% times 1 plus 10%, which gives you $133.10. And most of you will have immediately shortcutted that and said anything multiplied by itself 3 times we can simply raise to the third power. And so the easiest way to write that is going to be $100 times our factor, our growth factor of 1 plus 10% raised to the third power is going to equal $133.10. Now this gives us the general formula for compounding. The general formula for compounding is going to be the present value, the value at the beginning of the process, times 1 plus whatever the rate of change is. In this case, 1 plus the interest rate. And then that 1 plus the interest rate is raised to the nth power, which is why the exponent is outside of the parentheses. And that formula gives us the result of the future value. The abbreviations you see on the slide are standard abbreviations. PV will mean present value. FV will mean future value. N will stand for the number of periods. And I is going to stand for interest rate. Now really this formula works for any sort of a compound growth situation, and so I might be substituted by a number of different labels. You might see KE, you might see G, you might see the hurdle rate. You might see a lot of different labels used in there, but if you recognize the form that this takes, you'll be able to spot it and understand when there's some sort of compound growth going on. The opposite of compounding is called discounting. When we're discounting, we're really kind of taking the compound interest and backing it out of an amount so that we can see where we would have needed to start. Since compounding multiplies by 1 plus I raised to the nth power, discounting is going to do the exact opposite of multiplying. We're going to divide by 1 plus I to the nth power. So going back to our example that we worked on the previous slide, if you were to need $133.10 at the end of 3 years, and you can receive 10% annual interest, how much would you have to deposit today? You'd start with that future value, $133.10, and you back out the compound interest that you know will exist. So we're going to divide it by our growth factor, 1 plus 10% to the third power, and that's going to leave us with a present value of $100. So this brings us around to the general formula for discounting. The future value divided by 1 plus I to the nth power is equal to the present value. To summarize this, there are really 4 moving parts that we need to keep track of in compounding or discounting. There's always going to be a present value and a future value. There will always be a number of periods and a rate of return per period. And then we see the general formula for compounding and the general formula for discounting written out together. The only thing that's really going to be noteworthy in a compounding or discounting situation is how many periods the compounding or discounting is going on for. The more periods something is compounded, the greater that future value will be, and the more periods something is discounted, the smaller the present value would be. The power in compounding because it's an exponential function, is going to be the number of periods that we allow something to compound for. Something noteworthy, something that you want to write down somewhere, is that the rate of return is a per period rate of return. N and I are always kind of synchronized. If N is an annual number, I will also be an annual number. If we have 10% annual interest and we're talking about annual periods, that's fine. If we're talking about monthly periods and an annual interest rate, we're going to have to make some adjustments so that we come up with what the monthly interest rate would be. We're going to cover that in a few minutes. The APR is a label that you've probably seen or heard of before. It stands for annual percentage rate. For instance, if you see something which says 12% APR, that means 12% interest for the year. Now that's something that, as I said, we're going to have to make adjustments to if we're dealing with a non-annual compounding. So if interest compounds more frequently, we're going to simply divide that APR by the number of periods per year. So let's look at 12% APR compounded annually. We'd be looking at 12% interest per period. If we're compounding quarterly, we'd use 1/4 of 12%. Take the 12% divided by 4, we wind up with 3% interest per period. If it's monthly, we'd take 12% and divide it by 12 periods, because there are 12 months per year. We wind up with 1% interest per period. And if it's daily, we're actually going to divide it by 360. Now that's different than 365. There are a lot of reasons that get cited for that. The actual reason that it's used as an historic one, it's easier to do the math with 360 than it is 365. There are a lot of assumptions that we use in finance. One of them is, for example, that 3 months is 90 days, 6 months is 180 days. That means that 12 months would be 360 days. It's not entirely accurate, and a lot of financial services companies are now starting to use a 365-day year for their compounding. For instance, a credit card company is not going to give up those extra 5 days of interest every year. But historically, we've used 360 because the math was easier to do. Think about working something out with pencil and paper, or a slide rule, or a hand crank calculator like you might have seen in a movie. Something like that, using 360 is going to be much easier to work with. And traditionally, in finance, we still use 360 for a lot of different functions. If you run into a problem in a textbook which says that we're using an annual period of time in days, it will specify it if it's not going to be 360 days. If it's going to be 365, it will tell you to use a 365-day year. Now, the other thing to be careful of course, is 12% divided by 360 is 0.03% interest, but it isn't really 0.03. If you work that out on your calculator, you would see 0.03333333 repeating forever. So the little bar that's above the 0.03, the little bar above the 3 means that the 3 repeats infinitely. You will get a significantly different answer if you were to write down 0.03% interest than if you were to write down 0.0333% interest than if you were to use 12/360ths. If you were to put the fraction into your calculator and use that in compounding, you'd get a different answer. So let's look at the examples at the bottom of the slide. After 1 year, how much would $100 be at a 12% APR? At the end of the year, $100 compounded annually would give us $112. It would have our $100 principal, and it would have $12 worth of interest because we only have one compounding period. And you can see in the formula I've dropped out the plus sign. I've got 1.1200 to the first power. The first power is really just to illustrate that there should be an exponent there. Anytime you have something multiplied by itself only once, it's going to be the same thing as not having an exponent there at all. If we were compounding quarterly, it would be $100 times 1.03 to the fourth power. And that's going to give us 3% quarterly interest compounded 4 times during a year. At the end of the year, we'll have $112.55. Monthly compounding, $100 times 1.01 to the 12th power. That's 1% monthly interest for 1 year. Gives us $112.68. And compounded at the end of the day, remember we have 0.03% interest, so that's going to be 1.0003 raised to the 360th power. Now, if you've rounded that off to 1.0003 and you've plugged that into your calculator, you should be getting a different answer than what's shown on the slide. You should be getting a smaller answer. and that's because of the rounding error. If you were to put in 12 divided by 360 and then add 1 to that, and then raise that number to the 360th power and multiply that by 100, you'd come up with $112.75. Anything other than putting in that fraction, the way that it's shown up there in the purple lettering, is going to give you a slightly smaller answer than what would be accurate. The general rule on rounding in finance is that we want to round as late as possible. Modern calculators and spreadsheet programs like Excel are going to carry an awful lot of digits, and it's convenient for you to make use of that capacity. The tool is going to carry those digits for you so that you don't have to write down long numbers in your notes and then have to key in long numbers. But it requires you to kind of think ahead about what you're going to do with your calculator. So as I said, the order that I would do that in would be to take the 12 divided by the 360 and then let the calculator carry that number forward. I would add 1 to the result. I would raise the result to the 360th power, and then I would multiply that by the starting amount of principal, by the $100, and I'd get the correct answer. The effective annual rate is just the APR adjusted for the value of compounding. Sometimes you hear this called the APY, the annual percent yield. There was a time a couple of years ago that one of the local credit unions had billboards up, and they were advertising what was at the time a relatively high interest rate on an account, and it was, I think, a 4% APY. Obviously not a very high rate in general, but for the times that we were in, money market accounts were getting 1% if they were extraordinarily good. So a 4% APY was pretty good, but it was different than a 4% APR. Now, because the APY, or the effective annual rate, the EAR, is the APR adjusted for compounding, you know that that effective rate, or that yield, is going to be higher than what the nominal rate would be. In other words, the APY is higher than the APR. So if we look at the examples, 12% APR compounded annually is going to be a 12% effective annual rate. 12% APR compounded quarterly is going to be a 12.55% annual rate. And you'll see the way that I've computed that is to take 1 plus that quarterly rate, raise that to the 4th power, and then I subtract the 1 back out. The only reason that 1 exists is to make sure that our amount is growing every time. If you were to take something and multiply it by 3%, it would be a very small number. If you multiply it by 103%, it would show you the result, including compounded growth. So 12% compounded quarterly is going to have an effective rate of 12.55%. 12% compounded monthly would be 1.01 to the 12th. Subtract the 1 and we're left with 12.68% effective annual rate. And 12% APR compounded daily, we've got that 1.0003 with the bar over the 3, so it's the repeated number, to the 360th power. Subtract the 1 off the back end of it, and we've got 12.75% effective annual rate.